Welcome to Science After Dark. Today's episode explores one of the most unsettling questions in astronomy. If the universe contains so many stars, planets, and opportunities for life, why have we found no clear evidence of anyone else?
Yeah, it's a question that really gets under your skin once you start thinking about it.
It really does. So, for this deep dive, we are stepping into this profound mystery. It's an exploration we're calling Where is Everybody? The Fermi Paradox and the Silence of the Universe.
And, to truly appreciate the weight of this question, you first have to step back and just wrap your mind around the sheer incomprehensible scale of the cosmos.
Which is, almost impossible to actually visualize.
Right, exactly. I mean, if you just look at our home, the Milky Way galaxy, you're talking about this immense swirling disk containing somewhere between 100 billion and 400 billion stars.
Just in our galaxy, just in our local neighborhood, yeah.
Yeah.
And when you look out into the observable universe, there are hundreds of billions, perhaps trillions of other galaxies, each one bursting with their own stellar populations. But it's not just the physical size that matters here. It's the deep expanse of time.
Right, the universe is incredibly old.
Exactly. The universe is roughly 13.8 billion years old. Now, our solar system, by comparison, only formed about 4.6 billion years ago.
So we're kind of late to the party.
Very late. That means there are countless stars out there that are vastly older than our sun, stars that have been burning since the early cosmic eras. And around those ancient stars, we now know that planets are incredibly common.
Yeah, that's been a massive shift in how we see things.
It is arguably one of the greatest astronomical discoveries of our time. Virtually every star you see in the night sky likely hosts a planetary system. And many of these planets orbit within what astronomers call the habitable zone.
The Goldilocks zone, right.
Exactly, yeah. That perfect temperate distance from their host star where the physical conditions are just right for liquid water to exist on the surface. So not boiling away into steam, not freezing into solid ice, but flowing liquid water.
Which is what we assume life needs.
Right. So with all of that cosmic real estate, and with billions of years of a head start, the stage seems perfectly set for life to flourish, to evolve, and to spread. I mean, the universe should be absolutely teeming with intelligence. And this profound realization leads us directly to a legendary conversation that ultimately defined modern astronomy.
Oh, this is the Los Alamos story, right.
Yes. Let me take you back to a summer luncheon in 1950 at the Los Alamos National Laboratory. It was this casual gathering of some of the most brilliant minds of the 20th century. You had physicists Enrico Fermi, Edward Teller, Herbert York, and Emil Konopinski.
Just having a casual lunch.
Just a casual lunch, chatting about recent reports of flying saucers, actually, which naturally led them to a broader discussion about the probability of faster-than-light travel and extraterrestrial life. Now, Fermi was famous for his ability to perform incredibly rapid mental estimates.
Right, what they call Fermi problems now.
Exactly. So he grew quiet for a moment as he crunched the numbers in his head. Then, he suddenly blurted out his famous simple question, where is everybody?
It's such a simple question, but it just hits you.
It does, because what Fermi realized in that moment is the core tension of what we now call the Fermi Paradox. And it's important to understand for anyone listening that this is not a formal mathematical paradox.
Right, it's not like a glitch in a math equation.
No, rather, it is a glaring, almost haunting conflict between seemingly reasonable expectations and absolute reality. The expectation is that intelligent life should be common. And even if only a tiny fraction of those civilizations develop advanced technology, well, they should leave visible signs across the galaxy.
Like radio waves or megastructures.
Exactly. We should see their massive engineering projects, catch their radio broadcasts, or encounter their spacecraft. And yet, there is an absolute absence of confirmed evidence. The sky is completely, stubbornly quiet.
If this is just a conflict of expectations, how do scientists even begin to calculate those expectations?
Well, it's exactly like walking into an unimaginably massive, brightly lit stadium expecting a roaring concert, only to be met with total, eerie silence. You know the stadium is open, you know the conditions are right for a crowd, yet no one is in the seats.
Wow, that is a creepy image.
Right. So to make sense of this silence, scientists needed a way to organize the unknown, to take that overwhelming, terrifying silence and break it down into manageable pieces. And this necessity led to the creation of a famous mathematical framework in 1961 by astronomer Frank Drake.
The Drake equation.
Yes, the Drake equation.
Yeah.
Now, you have to look at the Drake equation carefully because people often misunderstand it. It is not a magic number generator.
You can't just hit equals and get a reliable final tally of alien civilizations.
Exactly. Instead, it is a framework for organizing our scientific uncertainty. It takes the massive, overwhelming question of, are we alone? And chops it up into a series of smaller sequential variables that we can actually analyze.
So what are the major unknowns in there?
Well, the equation walks you through the crucial steps required for a communicating civilization to emerge. First, you have the astrophysical factors, the rate of star formation, and the fraction of those stars that actually have planets.
Which we actually have some decent data on now.
We do, yeah. But then you look at the planetary environment, how many of those planets can physically support life? After that, we get into the biological unknowns, which are much harder.
Right, like how often life even starts.
Exactly. How often does life actually begin from dead chemistry? And if simple life does begin, how often does it evolve into complex life? From there, how often does intelligence evolve? And then how long do those technological civilizations survive?
I guess they could just wipe themselves out.
Right. And finally, do those advanced civilizations attempt communication? And do their signals remain detectable to us? For a long time, optimists just plugged hopeful numbers into these variables and concluded the galaxy must be packed with life.
But that's not necessarily the case, is it?
No, it's not. Recent analyses, such as those conducted by researchers at the Future of Humanity Institute, have taken a much more rigorous look at these uncertainties. When you input realistic uncertainty ranges, acknowledging that some of these steps might span multiple orders of magnitude in their unlikelihood, the math reveals something sobering.
What does it show?
It shows a substantial probability that we are entirely alone in the observable universe.
Does the math suggest our existence is just a statistical anomaly?
Well, I think we have to push back on the assumption that life is easy to make.
Yeah.
We often fall into the trap of thinking that just having water and a warm star guarantees biology.
Right, like it's just a recipe that bakes itself.
Exactly. But the transition from dead chemistry to self-replicating biology is incredibly complex. That mathematical realization that complex life might be astonishingly rare brings us to the first major explanation for the silence of the universe.
Okay, what's the first explanation?
It's known as the rare earth hypothesis. It proposes that while simple microbial life might be fairly common out there, complex animal life is exceptionally rare because it requires an incredibly unusual combination of factors.
So Earth isn't just a standard rock with water.
Not at all. We orbit a metal-rich star, which provided the heavy elements necessary to build a solid, rocky planet. And it goes far beyond just having the right rocks. We have a strong magnetic field driven by a churning molten iron core.
Which acts as a shield, right?
Yes, a planetary shield, preventing our atmosphere from being stripped away by harsh solar winds. We also have active plate tectonics. Now, this isn't just about continents moving around. It is a vital planetary thermostat. Plate tectonics regulates our climate over millions of years through the carbon-silicate cycle, trapping and releasing carbon to keep temperatures remarkably stable. Without it, you could easily end up with a runaway greenhouse effect, like Venus.
And we also have our moon.
Right, an unusually large moon created by a massive cosmic collision early in our history. It stabilizes the axial tilt of our planet. Without it, Earth would wobble on its axis, leading to chaotic, catastrophic climate swings.
Which would make complex evolution nearly impossible.
Exactly. So when you stack all these requirements together, it is entirely possible that the origin of life itself, or the leap to complex life, is extraordinarily unlikely without all these perfect, incredibly rare conditions aligning.
That makes a lot of sense. But there's another idea, right? Something a bit darker.
Yes, there is an even darker conceptual framework to consider, proposed by economist Robin Hanson. It's called the Great Filter. The Great Filter is a hypothetical evolutionary stage, a barrier in the development of life that very few worlds successfully pass.
Like a hurdle that's just too high.
Right, an impossibly high hurdle that filters out almost all contenders. And this concept presents two chilling possibilities. The first possibility is that the Great Filter is behind us.
Meaning we already passed it.
Yes, this would mean that the emergence of complex life, or perhaps the leap to human-level intelligence, is the incredibly rare step. If the filter is behind us, we have already won a cosmic lottery. We are the lucky survivors, and the galaxy is empty simply because no one else made it this far.
Okay, but what's the second possibility?
The second possibility is that the filter is ahead of us. This implies that life frequently evolves, and intelligent civilizations frequently arise on those billions of planets we talked about, but they inevitably face catastrophic risks before spreading widely across the stars.
Catastrophic risks like what?
They could be severe environmental collapse, planetary-scale warfare, the release of uncontrolled technology like runaway artificial intelligence or engineered pathogens, or simply resource exhaustion.
That is definitely the darker option.
It is. Now, we must present this carefully. Extinction is absolutely not an inevitable outcome, but it represents a gauntlet of immense challenges that every single technological species must eventually face and conquer if they want to survive.
If we were to find simple life on Mars, would that actually be bad news for humanity?
It sounds totally counterintuitive, but yes, think of it like a massive obstacle course where you do not know where the deadliest trap is located. If we find that simple life evolved independently on Mars, it means the early hurdles on that obstacle course are actually quite easy.
Right, meaning life sparks into existence frequently.
Exactly. But since we do not see advanced civilizations everywhere, it implies the deadliest trap, the Great Filter, is not in the past. It is still waiting for us, looming somewhere near the finish line of our technological development.
Oh, wow. That is terrifying.
It is. But what if civilizations do survive the filter? What if they make it past all the environmental and technological hurdles, and they are out there right now, yet we still cannot see them?
How would we miss them if they're out there?
Well, consider how difficult it might actually be to detect an alien civilization. We have spent decades listening for radio waves, but radio might be a primitive, inefficient technology that a society outgrows in just a few centuries.
So they might use communication methods we don't even recognize yet.
Exactly. Tightly focused lasers, neutrino beams, or operating on principles of physics we haven't even discovered. Even if they do broadcast, their signals might be incredibly weak, brief, strictly directional, or heavily encrypted.
Making them just look like random background cosmic noise to us.
All right. And we also have to think about timescales. Timescales are a huge factor here. We have only been looking at the sky with radio telescopes for less than a century.
Which is nothing on a cosmic scale.
Right. A civilization could have broadcast their presence for 10,000 years, but if they did it 2 million years ago, those signals have already passed us by. Two civilizations could easily exist in the same galaxy, but miss each other by millions of years.
Like ships passing in the cosmic night.
Beautifully put, yeah. Then we have the zoo hypothesis. This is the idea that an advanced hegemonic civilization, think of a galactic superpower, might deliberately avoid contact or observation.
Oh, like they're observing us from a distance.
Right. They might treat younger civilizations like ours as protected nature reserves, allowing us to develop culturally and technologically without overwhelming external interference.
That sounds like something straight out of science fiction.
It does, and it's a compelling narrative, but we need to clearly state for you, the listener, that there is zero empirical evidence confirming this idea. It is a pure thought experiment designed to explain the silence.
But there is a scarier version of them hiding, right?
Yes, a far more terrifying variation. Lou Sheckson's dark forest hypothesis. In this speculative scenario, civilizations remain perfectly silent, not out of benevolence, but out of absolute self-preservation.
Because the universe is dangerous.
Exactly. The dark forest treats the universe as a place of unknown, potentially hostile threats. Because interstellar communication is incredibly slow-limited by the speed of light, you can never truly know the intentions of a distant alien species.
You can't just hop on a Zoom call and negotiate a treaty.
Right, you cannot negotiate quickly or verify anything. Therefore, the safest strategic move is always to hide. Revealing your location by broadcasting a loud signal is inherently dangerous. It invites a preemptive strike from a civilization that decides it simply cannot risk leaving a potential future rival alive.
Would a truly advanced civilization really be hiding out of fear?
Well, imagine walking through a dark forest at night. You are armed, but you know the forest is full of other hunters. You do not know where they are, you do not know their technology level, and you do not know their intentions.
You just stay quiet.
Yes. In that survival scenario, every seasoned hunter knows the absolute best way to stay alive is to stay completely silent. If someone snaps a twig or shines a flashlight, they instantly become a target. But again, we must present this strictly as a speculative scenario, a game theory approach, rather than an established scientific conclusion.
It makes sense logically, but it assumes they care about the outside world at all. What if the most advanced minds in the universe simply lose interest in exploring the physical galaxy?
That is a brilliant point, and it brings us to the concept of turning inward. We naturally assume that an advanced civilization would want to expand, to conquer, to build giant starships and colonize new worlds.
Because that's what humans have historically done.
Exactly. But human assumptions about endless expansion, boundless curiosity, and the desire for physical territory may simply not apply to advanced alien intellects. As a civilization advances, they might turn their focus entirely inward.
Like retreating into virtual reality.
Yes, they may prioritize the creation of perfectly simulated virtual environments, immersing themselves in digital realities that are infinitely more malleable and satisfying than the harsh, cold, dangerous physical universe.
So they might not even have biological bodies anymore.
Right, they may transcend biological bodies entirely, becoming entities of artificial intelligence and prioritizing efficient computation over physical conquest. They may have absolutely no desire to colonize the galaxy because the physical universe is no longer relevant to their primary mode of existence.
That is wild to think about.
And building on this idea of computation is one of the most fascinating concepts in modern astrophysics, the Aestivation Hypothesis.
Estivation, like hibernation.
Yes, exactly. This theory bridges the gap between cosmology and the thermodynamics of computation. There's a basic principle in physics that processing information running computations requires energy and generates heat. Therefore, doing so is immensely more efficient in colder environments.
So the universe right now is too hot for them.
Right now, the ambient temperature of the universe is about 2.7 degrees above absolute zero, warmed by the cosmic microwave background radiation left over from the Big Bang. That sounds freezing to us, but to a super advanced digital civilization trying to run universe-sized simulations, it is actually quite warm.
But the universe is expanding, right?
Yes, and as it expands, it's cooling down. If an incredibly advanced civilization wants to absolutely maximize its computational power to run the largest simulations or process the most complex thoughts mathematically possible, they might choose to estivate.
Meaning they go to sleep.
Exactly. They would essentially power down their massive digital infrastructure and wait until the universe cools down in the incredibly far future. By waiting trillions of years for a colder cosmic background where the ambient temperature approaches absolute zero, they grant themselves a staggering exponential multiplier in their processing capability.
So they are just out there sleeping, waiting for the universe to freeze.
Pretty much. It is like carefully saving up all your money because you know the ultimate universe-wide clearance sale is coming in 1 billion years. The prices, the energy costs of computation, are going to drop to practically nothing. Spending your energy resources now in this warm, early epoch of the universe is just a massive waste of resources.
That is just mind-blowing. But even if some civilizations choose to sleep or turn inward, shouldn't at least one civilization have tried to conquer the stars?
You would think so. It only takes one expansive, physically ambitious society to fill the galaxy. So we really have to ask, how hard is galactic colonization really?
I mean, the distances are just massive.
They are. We have to examine the sheer physical barrier of interstellar travel. The distances between stars are staggering, almost beyond human comprehension. The nearest star to our solar system is Proxima Centauri, about 4.2 light years away.
Which would take us a very long time to reach.
With our current fastest spacecraft, it would take tens of thousands of years just to get there. The energy required to accelerate massive colony ships to even a small fraction of the speed of light is astronomical.
So maybe it's just too hard.
Well, despite these vast distances, there is a concept known as the Hart-Tipler conjecture that pushes back forcefully against that idea. This conjecture argues that even with relatively slow expansion speeds, a civilization wouldn't need to send massive colony ships with biological beings.
What would they send instead?
They could utilize self-replicating probes, often called von Neumann probes. Imagine sending an automated machine to a nearby star system. Once it arrives, it lands on an asteroid, mines the local metals, and uses its onboard manufacturing to build 2 copies of itself.
And then it sends those 2 copies to the next stars.
Exactly. They arrive, build 2 more copies each, and launch them. It is exponential growth. 1 becomes 2, 2 becomes 4, 4 becomes 8. Using this method of exponential growth, a single civilization could theoretically cross and map the entire Milky Way galaxy in just a few million years.
A few million years is nothing on a cosmic scale.
Exactly. And because a few million years is just a blink of an eye in cosmic terms, the tension of the Fermi Paradox returns with an absolute vengeance. The galaxy has been around for over 10 billion years. There has been ample time for a wave of self-replicating probes to sweep across the Milky Way dozens of times over by now.
But we don't see any of that.
No, we don't. The fact that we see no probes, no artifacts left behind in our solar system, and no signs of massive galactic engineering firmly reinforces the paradox. Perhaps long-range colonization is simply too expensive, too dangerous, and ultimately too unattractive, even for a super-advanced society that possesses the physical capability.
Are we simply rushing to conclusions based on a very brief period of looking at the sky?
We absolutely might be. Concluding that the entire galaxy is empty based on our current search is exactly like looking out your living room window for 5 seconds and concluding that bears do not exist anywhere on Earth because you didn't see one in your yard.
That's a great way to put it.
The bears have had plenty of time to wander by, but our observation window is minuscule. We have only been capable of receiving interstellar radio signals for a single human lifetime, peering into a galaxy that is billions of years old.
Which brings us back to our own solitary vantage point on Earth, just gazing out into the quiet dark.
Right. We are left suspended in that basic tension. On one hand, we live in a universe overflowing with potential billions of worlds, organic chemistry everywhere, and deep, deep time. On the other hand, we face a sky that remains stubbornly, beautifully silent. We've explored the possibilities that complex life is exceptionally rare, that great filters destroy civilizations before they mature, that aliens are hiding in a dark forest, sleeping to maximize their computation, or simply uninterested in physical expansion.
It's a lot to process, really.
It is. But as you reflect on the silence of the cosmos, consider this final provocative thought to mull over on your own. If humanity is indeed the first to survive this far, or perhaps if we are the only consciousness left in this entire corner of the cosmos, then surviving the great filter is not just about preserving human history. It is about ensuring the universe itself has a way to understand its own existence. If we fade away, the lights of consciousness may go out with us. The responsibility of the silence belongs entirely to us.